that going. And I've got everything. Okay. Hello, everybody. How's it going? Welcome to class today. I'm glad to see you all here, bright-faced and ready to go. I kind of left open Lab 3 if you wanted to look at that. We'll be doing that for the most part of today, as well as looking over some other stuff, functions, libraries, and some general Python style stuff. I want to start today with just a quick review of some debugging stuff, and also let's kind of open it up to any questions people are having over this the Drake equation program that we were writing from last time. On Wednesday, we worked on the Drake equation. It was about extraterrestrial life and how much might be out there. And it is actually part of Lab 3. You actually do have to have a complete working version of it. So now would be a great time to ask questions about that so we don't get too far behind on that one. Any questions on Drake? Yeah. Yeah, so if you try and input like 1/1/2 when like if you in like on the input function, I'd like to talk with Nick about this. Python will return 1/2 as a string, right? So if it asks what is R, and then you give it 1/2. What Python returns back to the program that you're writing is the string 1/2. And then you try and convert this to a float. But this doesn't make sense to Python. This as a string does not equal 1/2. This does not equal 0.5. You can do some weird things with eval or whatnot, but I would just suggest instead of putting in 1/2, just put in 0.5, and then you'll get the string 0.5, and Python knows what to do with this. It knows how to convert this to a float. So when you try and convert this to a float, it'll give you 0.5 as the float. Yeah, just try not to give it expressions. A lot of times with these earlier programs, we're just assuming that the user is giving us correct input, which when you start making more complex programs is a very, very, very bad thing to assume that the user is just going to give you what you want. You want to do things like checking to make sure they got the right stuff and whatnot. But for right now, we're just starting off. Other going to assume the users are good little dogs, and they're going to give us the right stuff that we need. Okay. Any other questions on Drake? That'll be due along with this lab, the whole thing. So, all right, let's get started today with where is it? All right, I need to make my text bigger. Let's go with 14. All right, can people see that? Can people see the text all right, big enough? Back? Good. All right, let's start off with just a quick little debugging exercise. Man, I hope this program called error.py works. Oh, wow, it didn't work. I wonder why. All right, so we've got our error message. And here's our program. Where's the bug? Let's hear from someone in the back. I never really hear from you three. Or at least I don't think I've heard three. Do you not like to debug? You shouldn't be in a computer science class. Let's hear it.
Is there missing a parenthesis on the print? Did you know that twice your age is? I can't see that.
It's trying to convert a string into a float.
Where?
The name is calling for a float input, and you're putting in the string.
Ah, okay. So I'm asking the user, what's your name? And the user gives me something that looks like a string, right? I'm trying to convert it to a float. That doesn't make any sense. Let's just go ahead and not do that. I didn't say to start anything. Okay. Let's do this again. To mark another error. Okay. There's the error message. Pretty good. I have a lot of Python stuff open right now.
Maybe between float and edge, input, you should put technical head.
Where?
And edge equals, like, parentheses.
And we could do int as well. We can convert it to an int or a float, whatever there. See if that fixes anything. No, now it's telling me I can't convert an int to a string implicitly. It's on line 6. Line 6. Yeah, Nick.
On line 6, you put in twice age, but it's an integer, so you can make a string.
Ah. Stir twice age. Beautiful. All right, let's try it now. My name is Mark. Did you know that twice your age is 44? Grant, good work. Just a quick little debugging refresher. Make sure we know how to read the error messages and everything like that. Pretty straightforward. Okay, you can see the bottom of the shell here. I'm going to try and bring this up a little bit. My computer's kind of freaking out today, so sorry if things get a little bit weird. Okay. So you remember the type expression that we used for some stuff the other day? When you use the type function here, whatever you put inside, it'll tell you the type of what you're putting inside. This is really great for debugging when you kind of are wondering, like, what does Python think I'm putting into here? So you can ask it for the type of whatever you put in, and it will tell you what the type is. Type function is great. You'll probably end up using that in the next lab. Now, there are some numbers that we can put into Python that look a little bit weird, that look a little bit different than normal numbers. So like when we put in 22 and it gives us back 22, we know what's going on there. But Python also understands little special expressions like 22E5. And this is sort of like some scientific notation sort of stuff going on. This is equivalent to 22 times 10 to the 5th. 22E5 is the same as 22 times 10 to the 5th. So this is just shorthand to help you make sense of really big numbers and to sort of scrunch them down. This will be very helpful when you get to lab 3 and we're dealing with stuff in the millions and billions, when we don't want to have to just type in this huge long number. We can just type in 22E5 and Python will understand what's going on. You can do it just the same way, just with everything else. You can do negative numbers, E negative 11, and it might just say 5E negative 11, but what that equals is 5 times 10 to the negative 11th. So imagine what that number is. I think you can out pretty well. So there's special numbers like that. And there's also some other little operators that we haven't gone over yet, like exponentiation. How do you take the square of something? And how do you, matter of fact, how do you take the square root? We're talking about both of those. So exponentiation is easy. You can just do 2 double star and then the power that you want to go to. So that's 2 to the third, 2 to the fourth. You can even do 2, 3e2, and you get something really big. So you can do all that stuff. So that's exponentiation. And there's one more operator that we haven't discussed that I want to introduce, and that's the modulo operator. Modulo operator is the percent sign. And what the operator does is it gives you the remainder of a division operation. So basically what modulo does is it divides and then it gives you back the remainder. So 4 divided by 3 is 1 point something, 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 right? But there's 1 left over after you divide 4 by 3. So that's what modulo returns. For another example, 10 divided by 6 would give you that. But 10 modulo 6 would give you 4. It gives you the remainder. What if you do 10 modulo 4? Well, it'll give you 2, because it goes 4, 8, and then there's 2 left over after the whole division takes place. So it always gives you the remainder of that operation. The most common use for this in computer science is figuring out whether a number is even or odd. You can do 6 modulo 2, 5 modulo 2, 4 modulo 2, 3 modulo 2. And what you'll see is that when you do modulo 2, it tells you whether it's even or odd, because even numbers return 0 and odd numbers return 1. So this is a really common thing to do for computer scientists if they want to figure out if something is even or odd. You just use the modulo operator in 2 to figure that out. But it's good for all sorts of other stuff as well. I figured I'd point that out there. You'll be using exponentiation and the special notation for E a lot in the lab, if you haven't already started looking at that. All right, so square roots. We need to know how to do those too. We were talking about this a few days ago, and someone was asking how you did that. And I described it briefly, but let's go more in depth. You might imagine doing something like square root 4 or square root 4 or something like that, right? You might imagine some sort of call here where you call square root and then you give it a number and it tells you that, right? But it's telling us that the name square root isn't defined. Python doesn't know what we're telling it here. Python does have a way to do square roots. It's just not immediately visible from what we're using right now. We have to make this square root function visible to Python by doing something called an import. An import. We have to import this particular function into our range, into our shell here, so that we can use it. And matter of fact, we don't have to import just square root. We can import a whole bunch of functions all at once by importing a whole library. Libraries are little repositories of functions and calls all packed together with a sort of common theme or something, but you can import them all at once and use them for whatever you want to. The module we'll be looking at today is math. And we make it visible or import it by using just the import keyword, the library name that we want to import. So I want to import math, and I can do that with the import. Doesn't give me any return value. It's just making this math module, this math library, visible to me. So I can use all of the stuff that's inside of this math library. Let's take a look at all of the stuff that's inside the math library. This is the Python documentation website. Some people call this like an API website or something like that. You can call it whatever you want, but it's basically a big old, it encyclopedia of all the stuff that's inside of Python and explanations of how it all works. It's a docs.python.org, all sorts of fun stuff in there. But in particular, here, we're looking at the page that describes the math library and all the mathematical functions that come with it. You might have to look up some of these along your way. And there's a lot of good information here about all of the functions inside the math library. You can see there's functions for getting the ceiling, copy sign, factorial, or fmods, so much fun stuff. And we can keep looking at all these and it will describe how all of them work and what they do here. Let's go to one that we're concerned with, math.square root. So what this is telling us right here is if we type in math.sqrt and then in parentheses we put in an x, it will return the square root of x. So let's try that. Type in math.squirt of 9, we get 3. Very fancy. And of course, we can do other things like math.log of things, and it returns the log of whatever we put in. There are some functions in here that have multiple arguments. So math.log here is an example of a function that can take in multiple arguments. We won't be getting too much into these multiple arguments for right now. You won't have to know them a lot, but it's important to note that you can put in more than one thing into this log. So one thing that a lot of people want to do with log is they want to change the base of the log that they're working under. They don't want to take I think this is log base. I don't know what the log base is for this one, but we can tell it to take a different base. So maybe I want to use log base 4. And I can use this notation for putting in multiple parameters, this comma, and then putting in another parameter to tell it what base I want to use. So I want to take the log of 10, but using base 4. And then we'll take the log of 10 base 4. So if you see things in the library on the website that look sort of like this, where they have this comma here, that means they take in multiple parameters. And sometimes they're optional. You don't have to put them in, but you can. And sometimes they're very much required. You have to put in both parameters. So, but you can explore that whole library on your own time. You'll mostly be using this square root stuff. Besides having functions, besides like stuff that does calculations, that does computations, it also has constants in the library. Things like pi and e. So we can ask for math.pi, and it returns pi. And we can do math.e, and it gives us e. These are obviously approximations of these numbers. They are, you can't calculate, well, supposedly you can, but there's an infinite amount of digits in pi, and we're only getting about like 15 or something digits in our approximation here. So it's an approximation of pi that Python is giving us, but it's sort of the best approximation that they can give, because computers can only understand so many digits at a time. They can't understand infinite digits. So we've got to use approximations. And this is a pretty good approximation to use if we're going to use one. So there's constants for you. And we can do those. So a quick note on functions. So when I've been calling math.square root and using these parentheses here, those parentheses after a name, so sort of like something that looks like a variable name, and then open and close parentheses. When I use that notation, I'm indicating to Python that I'm using a function. Stuff like input is a function, and print is also a function. They're just built-in functions of Python. And we're using extra functions provided by the math library here in math.square-root and math.log. Those are functions as well. The only reason I bring this up is because pretty soon you're going to be writing your own functions for Python, where you're going to be able to say something like, my function. And you'll be able to write your own function that will compute different stuff. Maybe it will compute, I don't know, maybe it'll compute somebody's chance that they're going to go to the movies today, or something like that. But you'll be able to write your own functions to do these sorts of things. So it's important to understand that what we're calling here are functions. We're going to be able to write our own later. But for right now, we're just using all of the functions that have been provided to us by Python and other libraries associated with it. Okay. Good. So, without further ado, let's start talking about Lab 3. This is what's going to be going on over the weekend, and we're going to come back on Monday and start to finish it up, start to get everything done. So some of you might have already taken a look at this already, but I want to kind of just go over it step by step to make sure we're all on the same page. So this lab is all about planetary motion and figuring out how far planets are from the sun and how long it takes a planet to go around the sun or any particular star that the planet happens to be orbiting. And with this information, we're trying to with this sort of information, scientists try and figure out what planets might be able to be habitable or have life, and what planets definitely can't, given this information. And there's two people that were very influential in this sort of study, Kepler and Newton. And they both came up with different equations for how to figure out how long it takes a planet to go around a star that's at. They came up with these laws of motion. So we're going to be discussing them and looking at them. The first person that you'll be looking at is Kepler. He created a pretty simple function for figuring out the orbital period of a star. You can tell, he figured out how to figure out a planet's orbital period from its astronomical units, AU. So the AU is measured in 1 AU being 149 million kilometers. That's kind of important to know. You've got to know that 1 AU equals 149 million kilometers, and you can plug that in to an equation like this. If you give 2 AUs here, then you know that you can do a little bit of algebra and what P is. Do some square roots, do some cube roots, whatever you need to do, and you can get our P. So the goal of this equation is to get P, the orbital period. And the orbital period is displayed in years here on this table. So what you want to do for this first part of the lab is you want to write a program that takes in certain AU values for the sun, like Earth is 1 AU, Saturn is this much, Mercury is this much, and you want to see if you can output the correct orbital period. All right, so if you put in 1 into your program, you should get out 1. And if you put in 9.58, you should get out the number on the right. So this is here to help you check your answers and to make sure that you're getting the correct stuff. You could check even further by figuring out the AU for a planet like Venus or something, and then seeing if you get the right orbital or the right orbital period. You can find that data on Wikipedia if you want to. But this table is just to test your code and to make sure you're getting the right values. This whole program should follow the same sort of format as the Drake equation that we were working on before. It should follow the general format of ask the user for input to input something like AU, and then you do your calculations on that input using this formula here, and then you print back the result, which will be the orbital period. So follow that same sort of formula we were using for the Drake equation, but now we're going to apply it to Kepler's law of motion here. And just follow the instructions. You'll be saving that file as orbitkepler.py there. Pretty straightforward. Any questions there? That's Kepler. So then it turns out Kepler didn't quite know what was going on. He didn't have all of the stuff he needed. So Newton created a revised formula to figure out orbital period, something a little more complex, a little more precise than what Kepler had going on. We present his here. The same sort of idea, you take in some input, some different variables, and you get back p squared, but we're ultimately looking for just p. You're going to be taking in the mass of the planet, mass of the star, and you should be able to figure out the rest of it from there. I believe that's the 3. I think it's 2, or you're taking 2 or 3 inputs there and solving it for the rest. It also comes with this constant g, this gravitational constant, which is 6.67 times 10 to the negative 11. Just note here that what you're doing with g is you're just multiplying this expression here by g. You're not really inputting any numbers to figure out g. G is just a constant. You're not doing any calculations to figure out what g is. You already know what g is. It's this number right here. And these are units it's expressed in. You don't have to figure out how to manipulate those units or anything like that. You just use this number like a constant. You just multiply it in here when you're looking at this function. Now, it's very important that you keep your units straight in this equation, that you keep your units straight. You'll notice just below, it says you've got to convert AUs to the appropriate kilometers. The kilometers measurement using the conversion of 1 AU equals 149 million kilometers. And you have to note also that this equation takes meters as an input. It doesn't take kilometers as an input. It takes just meters as an input. So you have to make sure you're converting all of your units to the right stuff, doing the right sorts of multiplications there to get the right results. You don't want to use just the AU input in here. You want to convert it to meters and then use it as such a thing there. So there'll be a lot of sort of unit conversion going on there. Yeah.
It doesn't say that you ever actually ask the user for an AU input. You just ask them for 2 mass inputs and just figure out the days.
You should also have to ask for an AU.
The name of the planet, the world, period, days, and masses.
No, your output is AU because you're converting for A, it gives back to you in meters, and then you convert it to AU, and it gives the definition of 1 AU as 149 million kilometers.
No. No. You ask for, I'm pretty sure.
I did notice in his eval that he had it mixed up, but given the steps he wants us to take, I don't think that's the case.
I'll take a look at it while we're working on it in class and figure that out. I'm pretty sure that you ask for AU and the 2 masses, and then you return orbital period.
But he doesn't give us AU, he gives us orbital period in days. So
Yeah, I believe you're supposed to go to the article to figure out to get the AU values. I'll check that during the class though and make sure I'm right on that. I will check when we're gonna work on this for the rest of the class, so I'll have some time to look at that. But yeah, I'm pretty sure it's AU. So yeah, you'll do that, and you're gonna check your data on this table, and you'll also have to check your answers by going to the Wikipedia page linked here. And you'll be scrolling down, and you'll be looking at, I believe it's this table right here. We're talking about these little planets here, these E, B, and C, and you'll be checking your answers given these known values here. We already know these values here, but you're going to be calculating them yourselves, and you're going to be seeing if your answers from the program match the ones found on this website here, on the Wikipedia article. And they obviously won't be exactly the same. Everyone has sort of a different slight calculation. There might be some rounding errors in the way we work with floats and whatnot. That's what these plus or minus means. Like your answer should be around 0.02815. It might be a little bit off, but it should be close. It certainly shouldn't be 0.04. It should not be that. It should be 0.02 something. Definitely pretty darn close to that. So you'll be doing that. You're also going to be doing where you'll be messing around with pi and how Python approximates that. You'll be seeing the difference when you use very crude approximations of pi versus how when you use very exact approximations of pi, you get sort of different results. And you'll be looking at that. And then there's sort of the standard lab evaluation. You'll be turning in all of your files, and you'll be writing up a Google Doc to share with Dr. Godrich there. There's also this part at the end about the Python style guide. Give us some time to work today, and then I'm going to spend the last about 5 minutes of class showing the style checker and how that works. So we'll get to that at the end of the day. The style checker is an important part, but we're gonna do that at the end of the day, and we'll also work on it more if people need to on Monday for that. So I think that's all I had to talk about with the lab. I'm gonna figure out that AU versus orbital period business and figure out which one exactly we're doing there. And yeah. Any other questions on what's going on with this lab here? Any other questions? Okay, good. Follow the general format that we worked on for the Drake equation, for that drake.py. Create a new script that will be storing your separate, that will be storing your Kepler and Newton variations. You want to store your Kepler and your Newton in separate scripts. All that jazz, but yeah, let's work on that today. Raise your hands with any questions. Feel free to ask me. I'm going to figure out this little period business. Good work.
So here for step 2, says the user will be asked after the name of the planet, the orbital period of the planet in days, mass in kilograms, sun in kilograms, the formula per second. Calculate the distance of the star from the planet next and output the result to the user, and then we have to convert it from meters to AU. And the problem is and also he gives us an orbital period in days, but the eval form asks us what are orbital periods in days. So technically, he's already given it to us. So I feel like he might have just made it.
Well, yeah. Let me see what I did. Yeah, you're right. I asked for distance too. There you go. Hopefully no one took a picture of that while I was showing. Yeah. Hold on 1 second. So I'm trying to, so you were. We are supposed to have.
Yeah, he gives it to us. And here is
think he wants to ask for he asked about for the date. So
It's one of them, but I have cross-checked my things using this, and they all have the correct. Apparently, my only problem was I was doing string astrometers instead of string astro, so I was getting it in meters instead of astronomical units. But now, when I solve for it, I'm getting the right output. So,
does it match the stuff the
Yeah.
AUs you see on the computer?
yeah. So.
Yeah, I was wrong. Nick was right. You're supposed to take, for that second Kepler part, you're supposed to take in the orbital period and the mass of the star and the mass of the planet, not the AU. You're taking in the orbital period for that one.
So then you have to solve.
Solve for A. Yes, correct. You're solving for A there. And then your results from your program should match the AUs shown here.
And so if we ask for it in days, that initial P in here is at the year. So if we ask for it in days, we have to convert it to years.
Yeah, it depends what you asked for. You should probably ask for the orbital period in years because, yeah, that's what the period is in the table. Or no, you're getting the orbital period in days. So then you have to convert that and do all the appropriate conversions to get it back to years. Yes. Yeah. Yeah. And then there's a typo in the evaluation. He asks, what are the orbital periods for planets E, B, and C? You should just replace that with what are the astronomical units, or yeah, AU for planets E, B, and C. Because that's what you're outputting with your program is the AU, not the orbital period. So that's a typo there. I'll have Dr. Gurridge correct that after class. But yeah, Nick, if you're done, you're good to go. Yeah. If you're done with the lab and if you're like good to go, don't have any questions, you don't have to stay any longer. Have you downloaded the style guide?
Yes.
Okay, and you've been able to run it, like actually like run it through Python. Okay, good. People get confused on that sometimes, so I was just making sure. Oh, I'm sorry. You don't convert the days into years. You convert the days into seconds. My bad.
Where would you plug that into that?
Your formula requires the period in seconds. So p squared in the Newton equation should be in seconds.
Oh, okay. So then you have to convert it back into.
No, there's no converting back into years. You convert it'll come into you as days, and it requires the period in seconds. So you get the amount of days in, convert that to how many seconds it is, and use that, and plug that in for p.
Okay.
Yeah. Sorry, I was going the other way around. Seconds. Yeah, you gotta convert AU. You gotta convert your meters that you get back from this equation into AUs. And then
lot of parents don't want to read all the parents close all the way to the end. I kind of like but you're not taking like graph C is a function. Yeah, but you want to use graphs just like pandemic. Because I'm very surprised on there was thinking like, oh, the graph C function, and then here's the input of the graph C function. So we gotta switch this back. Graph C you don't have to put inside. It would keep on just like trying to separate it out, and maybe separate it out into different lines, like solve the part of it on one line, and then another part of it on another line. You're taking in the orbital period in days and the mass of the two planets, and then you're solving for A. You want to return in AU value back to you, and that AU should match AU what's back.
So we're solving for A.
Yes, because A here is in meters, right? So the equation returns meters, and then you have to bring that back up.
Okay.
Yes. You've been finding your stuff as functions. Okay. So you're trying to control function. So when you define the function, and you try and run the script, it's not going to run the function. Right. So it doesn't load that. It's not going to try and function. Like, okay, here's this function called intro now. But they're just sitting in memory of Python waiting to do something. So right now, all this function will print this, but it doesn't know what calculus is. Never define calculus. You define it in this function here, but that's outside calculus. If you want to do it this way, want to do kind of the function here, you have to define how, you have to initialize the variable house first. And then you have to actually put in the value of house in the function that you have to call. So,
Do math clicks
these are the functions
call power
you just
from
define
other
the functions.
those and then put them
Take
there.
these functions, call and execute.
As like,
Now it's now
it's just like how many
initialize the variable called count. Now we're gonna define intro, that's define count, that's now. Oh, now we call it intro. Okay, now we've got to print this. Now we're going to count. Now we print this and this. So, and count shows up there. Now we know it's count. We got to change it. Okay. We're going to do those in class for a while, but do it that way. This is like,
Okay. With the last 2 seconds of class here, I'm going to show you real quick the Python style guide. I'll be showing this more on Monday, but I just want to make sure that you have sort of an idea of how to use it if you want to finish this lab over the weekend. So he has a link to this Python style guide on the lab. If you open that up, it brings you to a new web page that describes how the style guide works and whatnot. It's really helpful. It should help you figure out how to get the style guide. It's very in-depth about how to explain it. But the basic idea is you have to, the style checker is a Python program that you run, and it checks other Python programs. So eventually the instructions will take you to a page that looks like this. It looks like Python code because it is Python code. You have to right click on it and you have to save page as. And it's going to ask you what to save it as. You don't want to save it as a text document or anything else. You want to save it as Python style checker 3000.py. Make sure it has the .py extension or it won't be able, Python won't recognize it as a Python file. So you save that, the Python style checker. I already did it earlier. Come on. Come on. And then you should be able to run it. You should be able to open it just like any other Python file, and you should be able to run it. We'll ask you what file you want to check for Python style. If the file you're trying to check is in the same directory as the style checker, that is Python style checker.py is in the same folder as, say, your Drake.py or your Orbit Newton.py, all you should have to say is Drake.py. You just have to type in Drake.py, and it will run, and it will do all of its stuff. It's going to tell you a bunch of errors, and you can figure out what all of these, well, they're more like warnings, really. You can figure out what all these warnings mean from the website. The website will tell you what's going on there. So this is a quick example, just so if you want to look at that over the weekend, you've got it. So, weekend, everyone. I'll be here on Monday, and Dr. Goderich will be back on Tuesday. Woo! So much fun. Yeah.